future people, it is the 11th of March, 2024. Why do I always sound uncertain when I'm saying the date? It's weird, right? You think that that would be a thing I could deliver with finality. Um, let's have demos. Let's start with Zach. Zach.
Sure thing. I'm going to talk about the layer cache sign I implemented last week. So let's share a little code window. So this is in its own crate, the SI layer cache crate, and it's a 3-layered cache that is async friendly and doesn't use any locks, which is fun. It has a memory cache that is the Mocha lock-free concurrent hash map. And then it has a disk cache, which is handled by a database called SLED, which is a little experimental, but we're going to see if it works for us. And then it has a Postgres layer at the end. So the way that it works is, you look at here on gets, we check the memory cache, and if it's there, we assume that it's on all the other layers. We return it really fast. Then we take a look in the disk cache. This is some stuff that I was thinking about this morning that we should put this on the blocking pool because SLED is not async, although if everything's in memory, it'll be very fast, so you don't care. But if it has to go seek the disk, we should probably not keep our Tokyo executor behind for that. So yeah, so we look at the disk cache, and then if it's not in the disk cache, we go and fetch it from Postgres. And then you can see also when we get it, if it wasn't in the memory cache, we get it from the disk cache and then we write it to memory cache. And if it wasn't in the disk cache or the memory cache, we get it from Postgres, we write it to the memory cache and to the disk cache. That's how gets work. And then inserts are very similar. Where are my inserts? So except, yeah, so we look in the memory cache, we look in the disk cache to see if it contains it. And depending on the set of whether in memory or disk, we will insert it into the proper caches, and then we always spawn a Postgres write. The reason we always spawn a Postgres write is that it would be more expensive to do the check to see if it's there or not, and then write it, than it would be to just write it and let the on conflict do nothing handle it. So there's no reason to. We might maybe we'll add the check inside of the task it's in, and then we don't care, but. So that's the basic idea. So this theoretically will handle the storage for all of our objects in the new engine, and you'll be able to, if they're in the cache, they'll return very, very fast. And so that's the hope. And then if they're on the disk cache, they'll return a little bit faster. And hopefully we don't hit Postgres too much in our hot paths. So that's what will help us get fast.
Sweet.
Awesome. One thing I like about that is Victor and I ran into an issue with the content store. Whenever you'd write out, you'd hit all these conflicts, it'd wait back. So what we ended up doing was basically on conflict, do nothing, and just always like write and continue. So this is like the evolved idea of that, of any operation with the system should not have to do with writing out to the content store and blocking on it. So that's really cool to see.
Yeah. All right, Fletcher, you want to take the other side?
Yeah, okay. Because it's related. All right, so what I'll show is let's pretend like we have a system that's accumulating these new objects and we're writing into memory and it's flushing down. Wouldn't it be great if other services could benefit from knowing that a new object has entered somebody's cache? So if it's in your cache, it might be interesting to be in my cache. So we've started a little bit of work for that kind of emitting, publishing, broadcast mechanism to get content from one person's cache into another person's cache. So we're using some interesting tricks in Nats to do that, since we already have basically a network like thread that's already open to Nats. And we can't really guarantee the upper bounds of our message size. So it's pretty guaranteed eventually we're going to exceed whatever we configure our Nats max message size to be. So rather than worry about that game of brinksmanship, what we're doing here is making a little wrapper type like concern that'll segment up a large payload into chunks, a lot like TCP fragmentation of like a large thing into packets. The nice thing with NATs though, and specifically with the Jetstream part of NATs that we're using, is the order they go down the pipe is the order you get them out the other side. So the fragment reassembly that might be out of order that you might get in networking land is something we can actually, for the moment, utterly ignore because we get them basically ordered on the other side. So the code that's here is basically, that's like the sum total of the chunking. It was relatively painless and easy. And then on the consuming side, things got a little more fun. Like I'd say fun if you really enjoy Rust and state machines and failure scenarios and match expressions. So, but the important part for anybody looking at Rust is we implemented a future stream. So just like any NAT subscription yields you messages, it's the same thing. The only difference is we might have reassembled a large payload that's megabytes from fragments on the wire. So we're trying to be reasonably transparent, even to the extent of like propagating some of the acknowledgements for those chunked messages. We figured out a mechanism that we can sort of in batch sort of like acknowledge all those messages once we've buffered up enough contents. So what I'll do over here is just run our integration test. And what we're doing here is creating a Jetstream context. I'm going to talk like so much faster than that ran. We're making a Jetstream context for the purposes of the test. So kind of from nothing. So that was just a Jetstream stream. And then we're firing, I think, 10 megabytes of like a message body over there. And then concurrently, we're also waiting on that. So kind of at the same time, there's publishing and receiving happening. And so it's about 200 milliseconds or so. But again, that's also, we're paying all of the one-time costs of running the test, making a Jetstream context, subscribing to the thing. So my guess is like it is nowhere near 200 milliseconds. It might be like 50% or less. And we can figure out what the number was or what the number is going down the road. But at the moment, we kind of just want to know, is it going to be fast enough? And I think this is going to be fast enough without us even optimizing. I had about 2 or 3 ideas over the weekend that if we want this to go faster, we probably could. But it's kind of exciting.
So
yeah.
That's awesome. One question I had is, so it's going to process multiple chunks, yeah? And it's possible that chunks like 1 and 2 come in, but chunk 3, it's awaiting for a long time. The stream implementation will wait until all of them come, right?
That's right. So right now, what we did is there's a small amount of configuration on that client. So like how big the chunk size is, and everything else is you pass in a NATS Jetstream consumer. And there's where the tuning policy is. So if we know we're sending gigabyte messages across, we want to turn our like max unacknowledged message count way up, and we want to set our max age for those for that wait period. We want to like extend it. So that's like, I think, utterly tunable, assuming we know what size of payloads we're dealing with, and I think we're going to know that. So yeah, I believe our first test we did a gigabyte, but what that really means in the test for the purposes of verifying it is in memory on all of our laptops, there'd be a moment where there'd be 2 gigabytes of RAM being in use, and that seemed excessive for a test to prove that we can do it.
Yeah. Awesome.
Yeah, we will. It definitely would cause latency. So like the NAT's being used more as like a cluster hot cache backbone. Just it will move it locally.
Yeah.
Okay. Let's do John. John?
Hello everyone. My demo today is slightly different. Basically, I've been looking at instrumenting some of our integration tests so that we can understand how they trend over time. So this is what our old integration test output looked like. And you basically can't see much information without digging in. And even the timings are quite difficult to pull out. So I made some changes. So the first thing is that it outputs the logs in, well, it outputs like a JSON traces. I I'm not sure if that one was already there. Basically, it's emitting the test log as JSON in the log, and then the build kite collector collects it. So where I'm up to is basically I'm just making the CI changes so that it's actually consumed. But an example of what one looks like is like this. So you can see a test, and this is only a subset of some of our tests. And you can see duration and various other things. So pretty cool.
Super cool.
Yeah, what I'd like to get done is Fletcher and Nick helped me put some instrumentation into one of our integration tests, but we couldn't quite get the OTAL collector to collect it. But when that works, we will get span data inside our contextual test execution, which will be super cool.
Yeah, that's going to be so fun.
Yeah. That's it, really.
Thanks, Build
Just so we
Kite.
can trend performance stuff over time at a test level.
That's great. Let's do Nick.
All right. This is going to be a very very small PR. Not PR. Very small thing I'm going to show you. The asset picker's here, but it is now calling.
There we go.
It is now calling straight from the list schemas route, and you see it's list schema and not list schema variants. So we got multiple things in one with some work I've been doing. Number one, any concept of node add menu or menus at all are just completely gone from the system now. What's in place is now categories are directly on the schema variants. And what's returned from the back end is a more like real world route that actually reflects what's there. So instead of listing schema variant views, it lists schema views, which contain schema variants. And if you want to extend them in the front end, what you do is you go to whatever store you want to use them in, and you simply extend them. Maybe you want your schema variant to have, and the name's a little clunky, so I'm working on it. It's work in progress. Maybe you want the schema name along with the schema variant in the front end, so you just extend the existing type that you get from the back end that's a little more real world reflective. And then node add menu become category nodes. And like throughout this PR, there were some places that conflated schemas with schema variants and even components in some instances. So we split them apart, but this should reduce a lot of complexity when working with the front end, because now nodes and node add menus are not there at all. And you just use the schemas returned from the back end. And if you want to split your accessors and getters by schema or schema variant, you can do either or. So schemas will know their default variant, or you can group all variants together. You'll be able to work with both in the component store much easier. And that concludes my demo.
Nice. Fabulous. Victor?
Hello. Just a second. Okay, so the main demo I'm going to do today is related to connection annotations, and they're back basically, but there's like a few test cases, and there's one improvement that we couldn't sneak in the first time around, so we're doing it too. So right now the test case we've been using for connection annotation since the beginning was the yarns that I forgot what they mean. Whatever resource number in AWS.
I am role and task definition.
Yeah, no, what I mean is like, what does yarn mean? The
Amazon
letters.
resource name.
Amazon resource name.
Amazon resource name. Okay. AM role, and it's going to create a task definition. And you'll notice that there's an Amazon resource number coming out of here. And there's two slots, two sockets for roles here, and we can fit on either one of them. So yeah, connection annotations are back. Another thing that product decided makes sense is like when a connection annotation has two valid sockets to connect to, in the case where we're doing implicit connections, it shouldn't connect to any of them. So if we have an IAM role that is a downframe, right? So data from this socket would go to their children, and we drop a task definition inside. Let's make this into a it's not going to create any implicit connections because it has two candidates, but you can still do the explicit ones.
Beautiful.
Yeah.
That's such a smart solution to that problem.
Yeah. Yeah. Shout out to Paul. I was trying to convince him of like, oh, let's connect both, and you like the client can delete the thing. But that, yeah, there's more confusing than anything.
Yeah. Yeah.
And then just to preview that the thing actually works. So the IAM, if the IAM role is, where's the last? And now to prove that the implicit connection works when there is like only one candidate, we're doing a launch template. And an instance profile. Instance profile. And I don't know if anyone noticed, but like real-time stuff is back. So I'm not having to reload the page every time I create a component or anything. That's part of what came in last week too. Make this an up frame. We drop an instance profile inside of it. We're going to like get to single connection from this ARN. There you go, to the instance profile ARN. So yeah, everything's back, and now we have the implicit connections, which is something that we left out. And first time. There you go. Also,
Love
nodes
it.
are dead. We don't have node IDs in the front end anymore. That got merged. I think that warrants a.
Yeah, it does. Node IDs are dead. Long live component IDs. Okay. That was great. Future people, see you next week.